Imagine you're sitting in your living room having dinner with your family when the ground beneath you begins to tremble. The table and chairs shake violently, causing glasses to rattle and silverware to clatter against the plates as everyone instinctively grips the table to steady themselves. The noise from the walls, creaking with each jolt, mingles with the distant rumble of the world outside, which seems to roar with a primal force. If you live in a high seismic area like much of California, Alaska, or other earthquake-prone regions, then this scenario is not just a thought experiment, it's a potential reality. Your home, the place where you feel safest, is your first line of defense against the raw power of an earthquake. How well will it hold up when the ground shakes with unrelenting fury? Fortunately, if your home was permitted and built under modern building codes such as the International Building Code and the ASCE 7 standards, then it has been designed at least theoretically to meet modern minimum seismic performance requirements. These codes are crafted to ensure your home can withstand earthquake forces while balancing life safety with cost-effective design. But what does this really mean? How will your house behave when subjected to different levels of seismic shaking, from mild tremors to the rare, catastrophic quakes that codes are calibrated to address? To answer this question, we need to understand how the code characterizes earthquakes when it comes to the design of a home in a particular location. While earthquakes are often described by their magnitude, the building code's design framework is generally not based on a specific major earthquake. However, nearby fault zones that have been determined to have the potential to generate significant earthquakes are still accounted for in the development of the design parameters. The building code framework for seismic design is based on the level of shaking that your house expects due to ground motion at the site where your house is located. The ground motions may come from a nearby moderate quake or a distant major one. For example, a major earthquake with a 2,475-year return period occurring in Los Angeles might cause violent shaking in Los Angeles but barely stir the ground in Santa Rosa, which is in Northern California. So, when we ask what happens to a code-compliant home during an earthquake, the answer depends on the ground motions at the site and not just the size or name of the earthquake as reported in the news. This distinction is essential for understanding what the code expects your home to endure. The primary objective of seismic design under modern building codes is to protect human life. This goal is expressed through a calibrated framework that considers different levels of ground shaking. At the most severe level, the ground motions associated with the maximum considered earthquake, the structure must not collapse. This is known as the collapse prevention objective. At lower levels of shaking, such as those associated with the design earthquake, the structure may be expected to remain stable and allow safe evacuation even if some damage occurs. In this video, we'll dive into the fascinating and critical world of seismic performance, exploring how code-compliant homes, particularly light-frame wood structures, are expected to behave under different levels of ground motions. Our goal is to evaluate how homes that are built to meet the minimum code requirements will stand up to different levels of seismic shaking. It is important to note that modern seismic design intent, as reflected in today's building codes, began to take full shape at the beginning of this century with the introduction of the International Building Code. Homes and buildings permitted and constructed under the IBC, particularly those designed under ASCE 705 and later versions, are the ones that are most aligned with current expectations of performance across different seismic intensities. Therefore, our analysis assumes that the structure we are considering was built under these codes and fully meets or exceeds the requirements expressed in those codes. Structures which are designed under these codes but are not code compliant may not achieve the levels of performance that we are describing. According to the IBC, your home and every home around you is classified as a risk category 2 structure. A risk category is a classification that is assigned to a building or structure based on its intended use, occupancy, and the potential consequences of its failure during a seismic event or other hazard. The risk category determines the level of seismic design requirements, ensuring that structures critical to public safety or community function are engineered to higher performance standards than those with less societal impact. Your single-family home is designed differently from a hospital or a fire station because of its role in the community. Understanding these categories is crucial to appreciating how your home, as a risk category 2 structure, is engineered to perform under seismic shaking, and why some buildings face stricter standards. The IBC defines 4 risk categories, each reflecting the building's function and the potential impact of its failure during an earthquake. Risk Category 1 includes low-risk structures, like agricultural sheds or storage facilities, where failure poses minimal danger to human life or community function. These buildings face less stringent seismic requirements due to their limited occupancy and low societal impact. Risk Category 2, which includes most residential homes, apartments, and standard commercial buildings, assumes typical occupancy and focuses on protecting occupants while balancing cost. Your home falls here, designed to ensure safety without the heightened demands of critical facilities. Risk Category 3 covers structures like schools, large assembly halls, or power plants, where failure could endanger many people or disrupt community recovery. These require enhanced seismic resistance to protect larger groups and maintain functionality. Risk Category 4 is reserved for essential facilities such as hospitals, fire stations, emergency operation centers that must remain operational post-earthquake to support life-saving services and disaster response. These structures are engineered to the highest standards, with minimal damage even under severe shaking. Risk categories are vital because they align seismic design with a building's role in society. In a high seismic area, a collapsed home endangers its occupants, but a failed hospital could cripple a community's ability to respond to a disaster. By placing higher seismic demands on high-risk category structures, the code ensures that critical facilities can withstand stronger shaking with less damage. For your Risk Category 2 home, the code prioritizes life safety and collapse prevention, as we'll explore, but allows controlled damage to keep construction practical. This tiered approach, informed by decades of seismic research, ensures that resources are allocated efficiently, protecting lives while recognizing that not every building needs to perform like a bunker. Understanding these categories sets the stage for evaluating how your home is designed to handle earthquakes of varying intensities. Before we can fully understand how a structure is expected to perform during an earthquake, we need to take a closer look at the levels of seismic shaking that define the design process itself. The building code sets up a hierarchy of seismic acceleration thresholds that map out the intent of the seismic design process. Earthquake design starts with defining how intense the shaking might get at your site. The code begins at the top, with a level of seismic shaking known as the maximum considered earthquake. This is a rare and extreme level of seismic shaking that is strong enough to cause severe demands on a structure. We can visualize how high this can get by comparing it to vertical forces due to gravity. If we consider a random address in the city of Berkeley in California, we can see that the ground motions associated with the maximum considered earthquake have a peak acceleration of about 0.84 g, while the spectral accelerations that a typical residential building may experience can be as high as 2.38 g. In contrast, gravitational acceleration is 1 g. This means that 2.38 g is more than twice the gravitational acceleration. If we imagine a massive equipment that could rotate your house 90 degrees while holding it at the foundations, the pull from gravity would equal 1 g. That's the same force your house would feel if earthquake shaking caused the building to accelerate sideways at 1 g. You can see that this will put a lot of strain on the framing and connections. Now imagine what would happen if the seismic shaking produced accelerations of about 2.38 g. This is not even the whole story. Seismic shaking is a dynamic event, which means that the forces happen back and forth. The code does not expect buildings to remain undamaged at this intensity. Its only concern at this stage is identifying the upper limit of what the structure could be exposed to. To make the design process more practical, the code reduces this extreme level of shaking by 1/3. The result is a level of shaking known as the design earthquake, and it serves as the reference level of shaking for which the structure is engineered. For our random address in Berkeley, this is equivalent to 2.38 G times 2/3, which is 1.58 G. Even though this is a reduced level of seismic shaking, it is still relatively very high. Therefore, rather than designing the structure to resist the full force associated with the design earthquake, the code allows engineers to reduce those forces based on how the structure is expected to respond. The process of reducing seismic accelerations below those associated with the design earthquake is accomplished through certain key guidelines. The code requires engineers to use special systems to resist earthquake forces known as seismic force resisting systems. These systems are designed to absorb seismic energy and sustain permanent damage while protecting other elements such as gravity columns supporting beams whose failure may be catastrophic. This ability to respond dynamically to an earthquake while absorbing seismic energy and sustaining permanent damage is known as ductility, and the code recognizes it by assigning response modification factors to different systems. For typical wood-framed homes, wood structural panel shear walls are the most common seismic force resisting systems. Wood shear walls are assigned a response modification factor of 6.5. This allows the engineer to divide the design earthquake acceleration by a factor of 6.5. For our random address in Berkeley, this is equivalent to 1.58 G divided by 6.5, which is 0.24 G, which is about a quarter of the gravitational acceleration. What this means is that the forces used in actual seismic design are just a fraction of the forces implied by the shaking intensity associated with the maximum considered earthquake ground motions. This stepwise process from the maximum considered earthquake seismic response demands, to the design earthquake seismic response demands, and to the reduced design forces is how the code bridges the gap between real-world shaking and practical construction. We now have the full context of the seismic design framework that the code has built around a typical structure. Therefore, we can commence with our analysis of what to expect at different levels of shaking. Let us begin with seismic shaking associated with ground motions that result in building accelerations that do not exceed a sixth of the design earthquake. We are using a sixth of the design earthquake so that the level of shaking can correspond to the forces that a wood frame structure with wood shear walls is designed against. This is a situational benchmark that depends on the lateral force resisting system that we are using. This level of shaking corresponds to gentle tremors that might rattle dishes or cause minor swaying. At this levels, we can expect a code-compliant wood-framed home to sustain no permanent or even visible damage. While the code does not explicitly define that such a home should meet an immediate occupancy performance objective, we can conclude that a fully code-compliant home should be fit for continued use under these circumstances unless it has been subjected to other unforeseen situations or conditions. As shaking at the site increases beyond that design force level and approaches the full design earthquake acceleration, the structure enters a transition zone, which is a critical range between linear and nonlinear behavior. This is when the framing begins to yield, which means some elements are undergoing permanent damage. Nails in shear walls start to slip, panels deform, and small cracks may form in interior finished gypsum board at corners or around openings. Framing members may experience minor splitting, connectors begin to elongate under load, and tie-downs stretch slightly under tension. Inside the home, the signs of stress become visible. Light fixtures swing violently, and wall-mounted TVs and picture frames tilt or fall as cabinet doors swing open. Interior finishes may show signs of stress such as minor cracking around door and window frames, but essential exit routes remain functional. While some non-structural elements might shift or flex, the structure is expected to preserve safe egress and avoid life-threatening damage. While the building still stands strong and protects its occupants, it is no longer behaving as a stiff, undamaged building. It's absorbing energy through controlled, localized damage. The code anticipates this kind of response. It does not require that the structure remain unscathed or fully functional at this level of shaking. Instead, It allows, and even expects, some degradation in performance as the building works to survive stronger shaking. What matters most is that the structure remains stable, intact, and moving safely toward the performance level it was designed to meet. While the design earthquake defines the level of shaking a structure is actively designed to resist, it is not the end of the story. The ground does not stop shaking just because the code draws a line. Earthquakes can and do produce accelerations higher than the design level but still short of the most extreme cases. In the range between the design earthquake and the maximum considered earthquake, the structure is subjected to forces beyond those used in its explicit design. However, the code anticipates that reserve strength, ductility, and redundancy will enable the structure to remain stable and avoid collapse. In a wood-framed home, observable damage includes the continued distortion of shear wall panels resulting from walls racking more severely, causing more yielding, which leads to higher drifts. At the same time, gypsum board damage becomes more widespread. Even as this is happening, it is expected that the building should still stay standing. Seismic accelerations corresponding to the maximum considered earthquake ground motions and beyond mark the entry into a new ominous territory. At this level, the only thing the code demands is that the structure must not collapse. This is the collapse prevention threshold, which is the final line of defense. For a wood-framed home, this means the structure may be severely damaged, with major permanent wall deformation and some broken connections. Most of the hold-downs may have yielded at this point. Anchor bolts at the base of the wall are tearing through sill plates while the overall shape of the house racks noticeably out of plumb. Inside, nearly everything is likely to be in disarray. Cabinetry may have broken free and appliances might be toppled or destroyed. Utilities may be ruptured, and fireplaces or chimneys could partially collapse. At the maximum considered earthquake, the house may be uninhabitable, but it is expected to remain standing to allow the occupants to escape. While the maximum considered earthquake defines the upper bound for code-based design, ground motions above this level are still possible, especially in near fault zones or during highly localized severe shaking. At that point, the structure has gone beyond the design envelope, and collapse becomes a real possibility. While some studies suggest that a well-designed home with a fair amount of redundancy may still remain standing even when accelerations increase by 30% beyond those associated with the maximum considered earthquake, this is not guaranteed. Beyond this threshold, the code offers no promises. Performance depends entirely on the robustness of the structure, the quality of construction, and other factors beyond minimum code requirements. While this video has discussed the performance expectations for typical code-compliant structures, it's important to clarify that these expectations are based on the minimum requirements for risk Category 2 structures, which include most residential homes. These structures are designed primarily for life safety at the design earthquake and collapse prevention at the maximum considered earthquake. However, homeowners are not limited to these minimum benchmarks. If a higher level of performance is desired, such as the ability to use the home after a major earthquake with little or no interruption, then the homeowner can work with engineers who are well acquainted with performance-based design. Performance-based design gives engineers the flexibility to tailor structural systems and detailing to meet specific post-earthquake performance goals that go beyond code minimums. It is also important to understand that performance-based seismic design is a specialized area within structural engineering. Not all civil or structural engineers routinely practice this method, as it requires advanced knowledge in nonlinear behavior, seismic risk modeling, and often a familiarity with frameworks like ASCE 41 or FEMA P58. This expertise is typically found among engineers who regularly work on seismic retrofits, high-performance buildings, or essential facilities such as hospitals and emergency response centers. Homeowners interested in pursuing this path should seek out engineers with demonstrated experience in performance-based design or seismic resilience. To initiate this kind of design, the homeowner should first clarify their goals. For example, do they want the home to be livable after a major earthquake? Is protection of expensive equipment or valuable family possessions a concern? Once these objectives are defined, the engineer can then determine what system upgrades, detailing requirements and design tools will be needed to meet the performance targets. Of course, this enhanced level of seismic performance comes with trade-offs. The structure will require more robust lateral force-resisting systems that can meet the higher strength and tighter drift demands. There will also be more detailed attention to non-structural components and building contents. These upgrades naturally lead to increased construction costs. However, for some homeowners, particularly those with the means and a need for continued functionality or who conduct essential activities from their homes, this investment may be justified. Ultimately, performance-based design empowers the homeowner to go beyond life safety and pursue resilience tailored to their specific needs. If you have enjoyed this video, please don't forget to give it a thumbs up and subscribe to the channel, and do not forget to hit the notification bell so you never miss an update. Your support helps us keep creating great content, and we'd love to have you join the community. Thank you for watching.